Welcome to this brief presentation on the Occam process for electronic assembly design. The objective of this presentation is to provide you with an understanding of the process, as well as some of the motivations and potential advantages of using the Occam process in future electronic assembly manufacturing. The current paradigm finds the industry with three basic manufacturing industries: those that make electronic components, those that make electronic interconnections, such as printed circuit boards and the like, and then the EMS or electronics assembly industry, who do the soldering and the joining of components to substrate and potentially build boxes and the like. In the past, vertically integrated companies did all of this under one roof, and there were some significant advantages for doing that. There are ongoing challenges in terms of the assembly, as electronics have historically tried to increase the functionality while reducing size, weight, and cost. One of the challenges in the manufacturing of electronics today is that lead pitches are decreasing, which makes it much more difficult in terms of the design and the assembly, especially below 0.5 millimeter pitches. Product life and reliability are being impacted by choices such as lead-free solder. The supply chain is growing more difficult to manage, and lead-free is, as I said, causing some concerns about cost and reliability. Soldering is not a simple process. Here's an example of a fishbone diagram, which illustrates just how complex and how many different issues there are associated with soldering and different things that must be controlled. When it comes to soldering, there are lots and lots of different kinds of defects that are illustrated here, both photographically and descriptively, giving you an appreciation of what is the challenge associated with soldering. Moreover, solder process generates prospective defects in the printed circuit boards as well, in terms of corner cracking, barrel cracking, delamination, pad grading, and with the advent of lead-free solder, even the decomposition of the polymers used in the manufacturing of the printed circuit boards can be problematic. So the Occam process, the fundamental objective is to reduce complexity in manufacturing by eliminating solder in electronic assembly. An abbreviated description of the Occam concept is to position and bond various tested components on either a temporary or permanent carrier, encapsulated the components in place. If you're using a temporary substrate, remove them from the substrate and expose the terminations, and then interconnect those terminations using long-held technologies of additive and semi-additive or some alternative direct interconnection methods, which we'll talk about shortly. Here's what that basic process sequence looks like from top and then up and then down again. It shows examples: components placed, encapsulated, the assembly flipped over, access to the features, the terminations on the components is done, and then a number of layers, these processes are repeated until the number of layers required are achieved to make all the interconnections for the electronic. If you look at conventional electronic assembly, SMT assembly, there are a number of steps that are required, certainly beginning with a schematic, the design of a printed circuit board assembly, design of a printed circuit board, and then going through the processes to manufacture the various elements in assembly. Looking at the Occam process, which does not use solder, you can see there's a significant abbreviation in the number of manufacturing steps required. Looking at this in terms of description of process, there's a lot of things that consistently need to be required from the design side, just creating the schematic and identifying the types of components that are used. Then you have a number of manufacturing steps depending on the complexity of the printed circuit board. And then finally, there's the assembly steps, of which there are many, and often electronic assemblies go through multiple cycles of assembly. So by reversing the assembly process, it can help eliminate many of those manufacturing steps. As stated earlier, you just simply place the tested components You encapsulate them, you expose the terminations using one of a number of methods which we'll talk about, and then interconnect those terminations using an additive process. The result is that in an Occam manufacturing process, um, you see a significant reduction in the number of process steps that are associated with. So these areas that are blacked out are manufacturing steps that are no longer required. There are still shared steps, but this represents the opportunity, and it is one of the aspects that allows for one to achieve significant cost reductions. So the Occam approach has some novelty, but not the technology. The components can be placed conventionally. There's lots of suitable encapsulations in terms of coefficients of thermal expansion, shrinkage, conductivity. There's molding technologies that are available, lots of methods for being able to make the via creations. Semi-additive process fabrication is well established. Lots of new materials are coming online. Potential for building an all-copper system, and it's appropriate for all classes of products. One question that comes up is a concern about testing and rework, especially when you're encapsulating the component. But one needs to ask themselves, why do parts fail and what are the causes for rejects? At the end of the day, it's going to be controlling of the process that makes testing important at a certain level, but on the assembly side, you just focus on the manufacturing processes that are simpler and easier to control, and as a result, the product should be easier to build. So here's a benefits analysis for Occam, starting with the elimination of the printed circuit board. The interconnections are still required, but they're done in situ. So you don't have to have a printed circuit board and test it and qualify it. You don't have to inventory it. You don't have to go through concerns about shelf life concerns for its solderability. There's no concern over conductive anodic filaments, which are becoming more problematic as lead pitches come down. No surface durability concerns. You're not going to experience any high temperatures, which can cause components or to warp or printed circuit boards to be damaged. And then there's lower overall material use, which will also help on the there's no soldering required, so again, that eliminates all the manufacturing steps that were just described, and no soldering related defects or failure, none of the damage that was described, no solderability testing, no concern about RoHS restricted materials, especially lead, no conflict metals or materials are used in this. The energy consumption is significantly less, and post-assembly cleaning and cleanliness testing are obviated. There's reduced concerns about the components. Only tested and packaged components are going to be used. There's no solder buildup on the testers. You don't need to worry about coplanarity of leads. No surface finish concerns. We're looking at ultimately, and this will be explained in more detail, but fewer types of components. LGAs and QFNs are the preferred ones. This allows you to get to a smaller component library in terms of packaging type, and you can get simpler, lower cost and higher yield on devices. Moreover, there's no concern about moisture sensitivity levels or popcorning, which happens at higher temperature soldering. And improved routing for IC packages, even the potential for overlapping components is possible. And here's an example of what that looks like, shown from the bottom, where components are existing in the shadow of the components above them, or in this case, it would be beneath them, and the ability to route a higher density assemblies than are done presently. Occam benefits also design simplification, is that the components can be placed closer together, and that routing capacity or capabilities are greatly improved. They're improved by such things as the routing reduction and layer reduction using techniques such as the IMPS, Integrated Power Mesh System, which was developed by Len Schaefer and his colleagues at the University of Arkansas, and also used in some designs at Hewlett-Packard. This slide courtesy of Happy Holden, whom many of the listeners probably are familiar with. Here's an example of some of the routing advantages. Once you no longer have to concern yourself with putting a solder component, it improves routing channels because the access through the polymer layer above allows you to route directly over terminations without a concern of short. Same thing happens with area array routing, is that without making, in this case, an area array device that would be, say, a solderable, one where required soldering, you can route even closer than you can, or you can do more routing between. And there are some significant advantages of that, which will be described here in a momentarily. So one of the things that has been problematic was the design of what has been called, or the approach which has been called the 80% design rule, which was adopted in with the advent of surface mount. From a road mapping perspective, designers decided that, or component developers decided that each new component termination pitch would be 80% of the pitch before. So starting with, for example, 1.25 millimeter, the next pitch would be 1.0, then 0.8, then 0.65, then 0.5, then 0.4. And so you wind up with a myriad or a number of different lead pitches. And this makes the routing of the assembly very difficult because you have to burn off layers to do the redistribution from layer to layer. And so I'm going to argue here in a moment that it makes more sense to adopt to a fundamental grid. And that single grid pitch looks something like this. Now these dots only represent a place or an opportunity, but every one of those is on a grid. And if you use components that also have their terminations on that common grid, you get a significant advantage in terms of routing. And this will again be shown in a little more detail clearly. But the examples here is that you're going to have to place components further apart when you have to do the redistribution. You have to add layers to do the additional redistribution. And perspective or potential for doing everything on a common pitch greatly increases routing facility. Here's an example of a slide showing the relative price index for an 8-layer for HDI type structures using the structures that are currently used for making assemblies. And here's the example if you go to an Occam type assembly. And you can see the significant reduction in terms of overall cost here. Reduction in cost and as well a significant increase in terms of density, in terms of terminations per unit area. Another aspect of this, which we'll talk about in a little more detail, is one of the problems that has occurred within industry, and it's been a knee-jerk response, is to come up with all kinds of different package thicknesses for different registered package types. And you can see here in this graphic that there's a whole lot of different package thicknesses. Moreover, those package thicknesses come in ranges. And the necessity for them to be in ranges is arguably a moot point, is that they could be a standard thickness, and that would greatly facilitate the Occam approach to design. And which one is it? Well, one can be somewhat ambivalent into which one is chosen. Perhaps it's a 0.5 millimeter thick, perhaps it's 0.8 of a milliliter. But whatever the pitch is, or whatever the thickness is inconsequential. It's just that it makes it easier from a design standpoint and manufacturing and assembly if all the components have a common thickness. So here's a slide I created, 25 years ago, 20 plus years ago anyway, which talks about the electronics future, which looks a little bit like Legos. These components, in this case Lego components, all have a common size, they all have a common termination, and the layout of the structure becomes much more easy to structure for now and in the future. So the hope is that when I get to the end of this presentation, you'll understand and appreciate just exactly how that works. So again, from a design simplification, one needn't be concerned with continuing down the list there. One needn't concern themselves with dead leads, so that opens up routing. From a design security standpoint, with all the components completely encapsulated, it's difficult for someone to disassemble or just look at an assembly and reverse engineer it quickly. Not that they can't be done, but the design will be much more secure, and it will also eliminate the concerns about people using pulls to provide counterfeit components or second use of components that are going to be lower reliability. The potential is to build an integral heat spreader, which will also provide increased density from a thermal management standpoint. Simpler, faster reconfiguration. Completed assemblies can be interconnected, as I'll show. It's adaptable to optoelectronics and can be used with flexible circuits. So here's some stacked assemblies, and as if you look at the cross section on the bottom, there's a potential for being able to put optical channels directly into the assembly, and then create interconnections, vertical interconnections, including a mezzanine connector for these assemblies. So there's a significant amount of advantage potential that needs or could be explored for these types of assemblies on into the future. Reliability is very important, and it is arguable that with an Occam type assembly, reliability will be greatly improved. These are simpler structures with fewer elements. They use lower temperature processing, which avoids the thermal damage associated with solder. Components can be fully encapsulated, and to increase their immunity to shock and vibration. You can create assemblies that are hermetic or nearly hermetic by completely overplating the final assembly with metal. Moreover, that step would provide total EMI or ESD protection. And again, that notion of integrating a heat spreader can extend the life of components, which there's an inverse relationship between thermal excursion and the life of transistors in integrated circuits. So here's an example of how a structure might be provided with a post-assembly thermal management structure. That's an advantage here as described, is that being able to address on the front end some of the concerns associated with heat removal, is that it can be done much more, rather than as an afterthought, it can be done on the front end. So aluminum is a substrate that I'm considering very important. It has lots of attractive attributes. One is that it's the third most abundant element on the planet, and about 8.3% of the Earth's crust. It's non-toxic, environmentally friendly. It's very low cost at about 72 cents a pound last time I looked. Very good thermal conductor at 200 watts per meter Kelvin. Relatively lightweight. It's 2.8 grams per cubic centimeter versus 1.85 for FR4, so it's slightly heavier, but the amount of material required should be significantly less, so that could be a wash. It is a metal, so it is dimensionally stable, which when you're building composite materials, there's always a degree of uncertainty. It has a CTE that is relatively closely matched to that of copper. It can be processed simply using machining, punching, chemical milling. You can anodize it to form an alumina on the surface. You can also electrophoretically or electrostatically coat it with epoxies to put an insulating layer over the top of this thing. What are the limits? What limits the use of aluminum currently? Well, one of the concerns with is that thermal conductivity makes it very difficult to solder using traditional soldering methods. You go to one extreme, on the low end, you're going to get cold joints, but if you go to the higher extremes required to get to the soldering temperature to get a reliable joint, then you're going to have a long or excessive thermal dwell, and it's going to damage the components. So with the notable exceptions, such as LEDs, most designers have determined that traditional laminates were better that serve their purposes. However, aluminum in the structures that I'm going to show you, I think can be used very effectively. So here's an example, taking a piece of aluminum, machining cavities into it, having components of common height, then drilling holes if you're going to provide access from one side to the other, filling those holes with insulating materials, coming back, drilling holes through the insulating material, and then overcoating the entire assembly with polymers top and bottom, and plating the circuit patterns up to interconnect the components on both sides of the assembly. Here's what that looks like on a one-sided type assembly is the idea starting at the lower left, machining aluminum, again, placing the components into the carrier base, encapsulating them, and then building up whatever layers of circuitry that are required to make all of the interconnections for the assembly. So Occam can also be used effectively with direct write technology. So here's an example of that, taking the components, placing them into a carrier, controlling the depth. If the depth of one component is a little bit lower, you can actually machine to a depth that is going to be appropriate for the components. And then simply printing out first a layer of insulator, leaving access to the features where you want to make terminations or electrical interconnections, and then printing down in case say a conductive ink, printing down another layer of insulator, providing again access for the features of interest, and then printing another layer of conductors and repeating this until you get a sufficient amount of layers to make all the interconnections that are required for the assembly that you're working on. So here's the design exercise I spoke of. This was work done by Darren Smith, a very talented designer on the East Coast. Here's an example of a design which he did previously. I suggested to him, do a redesign of something you've already done. The only thing I asked him to do in his redesign was not to go to look at a catalog for components that all have a common pitch, but pretend like those components already exist with a common pitch. The centerpiece on this is a 442 pin FPGA at 0.8 millimeter. On the right is the redesign of the structure, and you can see that the layer count is now 6 layers. It's a rigid flex assembly. It's about 40 by 30 millimeters when folded, and uses the same design rules in terms of line and space as the previous one. And so that comparison, again, the design is about 70% smaller in terms of total area. It folds into an assembly with a footprint about 15% of the original design. Although the density of aluminum is higher, the overall weight should be significantly lower, and the rigid flex structure allows you to do the separation of digital and analog circuitry, and the potential for better control for analog and power devices. So in summary, the Occam process sidesteps nearly all the problems associated with the traditional soldering process. Assemblies can be made smaller, lighter, more reliable, and less expensively due to the limited or reduced number of steps and less expensive materials. To this end, an Occam Prize has been created to incentivize the electronic assembly designers around the globe to explore for themselves the potential for the Occam process in products of their imagination. So with that, I thank you for your attention during this brief presentation, and I hope that this will inspire you. I invite you to read my text on the subject. It's called Solderless Assembly for Electronics, the Safe Approach, and that's available for free download, and there is a link provided within this website. So again, thank you for your attention, and I will hope that you will find some benefit from the lessons you've learned here.